Got it. Okay. Hello, everyone. A very warm welcome back to SMCB platform. After 3.5 months, we had last lecture on 19th of February. After that, we are again meeting here for a set of lectures on statistical mechanics, understanding time-driven statistical mechanics, en route to fluctuation phenomena and spectroscopy. Professor Bagchi needs no introduction. We are just waiting with our pen and paper to have a shared learning experience for the next 60 minutes or so. Professor Bagchi, please.
Okay, good afternoon. I'll tell something Ronjit later, something Peter Rollins told me, but it's not for public consumption.
Okay.
I wanted to tell you that, but I forgot. Okay. Because we just very busy last few days in working out something on time-driven stat mac on Maxwell-Boltzmann. And we just submitted last night, actually not last night, 2 o'clock in the morning today. So we have been very hectic time. So the idea of this came, I don't know from whom, but probably quite some time ago, I was mentioning to Sumon a need for understanding the continuity of time-dependent statistical mechanics, that it's a beautifully connected subject built by the smartest of the people. And so then I think that in that discussion, the idea of a course came out. Then it was a course of, I think, 1.5 hours. But when I started preparing the course, as I'm writing a book on this subject, which is nearly done, but you know, book is never fully done. This is the 4th book I'm writing, or 5th, and it doesn't get really done. So you have to abandon it at some stage. But anyway, so then I realized that the continuity of the subject that I'm talking is requires several things to be brought and which are not taught. Why they are not taught? I think they are taught in, but in our time we had this thing called pass course, honors, chemistry honors or chemistry major. Students somehow do not, many of the very interesting mathematics and physics courses that one needs to take to understand, they come a little later. Like probability theory was our 3rd year chemistry. And first years, 2 years were matrices, calculus, differential and integral calculus. And by 3rd year of BSc, we did not, by that time we were full in chemistry and it was very demanding. So we did not pay proper attention to probability theory. It is only after going to the United States when I started my PhD, and I don't know why I took so many courses on probability theory, that really even now I look back, eludes me, because I even took a graduate level, math department graduate level probability course. And where my colleagues and my students, their friends were just appalled that a chemistry guy taking this course. They openly wondered why a chemist would need such a course. But it's really, I audited that course. After some time, I found it difficult. But before that, I took several courses. But I found that whatever I have done, probably 50% goes back to my probability training. So probability is not taught. In fact, students don't even know how to think in terms of probability. But that is one of the connecting threads. There are many such connecting threads that need to be built in. So, and at the same time, one has to keep it somewhat interesting. One cannot do too many derivations, too many calculations, but that I can avoid because we have, as I said, we have almost finished product on non-equivalent StatMath, which we can send to those who want in due course of time. And that my current students, Shubhajit, Shubham, or Shangita, can, if you contact them, they will be able to send you these chapters. There is now book is 800 page and 33 chapters, and it's a thing which is really keeping me and many of my students really busy. So that so what I'm going to tell is kind of related to that book or motivated by that book, and that book will still probably about 6 months to 1 year in coming, and it will probably be submitted in a month or two. So in this course, this is the background of the course, and we'll see how it goes. Only thing I can tell that it will be very heavy on that continuity. It will be heavy on concept, and I recommend you that you get the books, read the books. So let us start. So layout of this short course is that one part will be today. I hope to go through this, what we call preliminary. So the book is divided into about 6 or 7 major parts. One of them is preliminaries, where you see here is the preliminaries, then which will be due today. Next part is the fundamentals and formalisms, which is a heavy thing, and where with the level equation, position of a technique, applications, position of a technique, then time correlation function, then moments and cumulants. That I don't know how I would do it because I have not planned it yet. It's a very, very sophisticated and heavy. Third is what I call my part is phenology. That's where your random walk, Langevin equation, Fokker-Planck equation, and all those things are there. That's in phenology. Then comes quantum dynamics, one big part. That's fifth part. Fourth part are certain applications, and which means phase transition kinetics, what you have learned in the other previous chapters. But so that's the kind of a layout of the book, and it's as I told you, it's a heavy course, just like my equilibrium StatMath, which I don't think anything like that existed. But in that case, at least there's some things. But in non-equilibrium StatMath, I found no help from any book. Even Zwanzig's book is not really very, it's not a text kind of a book, not a formal structure is not there. Why he didn't do it, I don't know. I just think he didn't have the patience. Van Campaign is beautiful book, absolutely beautiful book, and many very nice things are there. But then again, it is somewhat on a mathematical physics, stochastic processes side, which may in our study of chemistry and biology, that is not that helpful, as I'll discuss. So that is the background that where I tried to construct a course. It's certainly not one semester course, it's at least 2 semester course, at least. So that is the background. So we'll have the tools, and as I say, tools is the probability theory, and I very strongly recommend people to do probability theory. We'll do a little bit of that. The concepts, the relation between theory and experiments, that is a very important thing, essentially to motivate. Then birth of time-dependent, modern time-dependent StatMath, that I don't know, 3 or 4 which will come before. Here, how I wrote the slides, I don't remember. Then force and flux and Onsager's regression hypothesis, then hydrodynamics and Rayleigh-Bellon scattering, and kinetic theory of gases. So ultimate goal of theoretical research in chemistry is to understand the macroscopic properties starting from intermolecular interactions. And in this broad goal, which is very ambitious, this is developed by Maxwell, Boltzmann, Gibbs, and of course, I forgot to mention, of course, Einstein, and aided these days by computer simulations. And but you have to understand that the basics, we have a goal that we start only with essentially two ingredients. One is size of a molecule, the diameter, and the energy parameter. So there is a length and there is an energy. These are the only two things that you have. So starting with these two, you are going to explain, set out to conquer the world. Set with these two, or maybe one charge or W going to add in. You try to now explain the structure of a protein-DNA interaction, how an enzyme stops and begins production of, interact with DNA to turn off production of proteins, how that is connected with cancer, and like a lot of work now going on whatever on cancer cells and all these things. It's amazing that what is your canvas? Canvas is enormous. See, quantum people don't have that canvas. They are doing wonderful work and giving us intermolecular interactions and very nice things. Ab initio is a great thing to do. But the goal is not that, not yet at least. Okay. But in our StatMag, the goal from the beginning is very formidable. Not just liquids, phase transition, nucleation. These, of course, are always there. Now, in the basket, we have put in much of biology. The things like one does allosteric regulation, motor protein, and all these things. So, I think I want students to be a little aware of the challenge at hand and the kind of landscape. What we do bread and butter, which often are very small things, but we are part of a very big egg. So these are the two books. I have an NPTEL course on equilibrium StatMag, which is the link is given here. And the equilibrium StatMag book is out for a few years. They told me that they're going to make an Indian edition several times. Last time, I think in the middle of pandemic, they asked me, do I want a second edition or an Indian edition? I said, I want Indian edition. They're supposed to do God knows what's happening. The second book also will be CRC Press, is the one on the right-hand side on non-equilibrium StatMag. I given an arrow between them because I will link the two. To me, they are connected. So what do we do in equilibrium StatMag? Okay, there's time-dependent statistical mechanics, as you call it, on non-equilibrium statistical mechanics. That's one of the major things is the spectroscopy. Huge amount of physical chemistry spectroscopy, whether it's infrared, Raman, vibration, different forms of vibration relaxation, or these days on the time domain techniques, many orders, third, fifth order experiments. Then we do liquid state dynamics, of course, relaxation phenomena. We do biology, the physical biology, protein DNA interaction. We have to do binary mixtures, a very important industrial thing. Then, of course, chemical kinetics, which is the goal of chemistry. So there are huge number of things where equilibrium, non-equilibrium StatMag is important. And how do we do it now? There is a formidable flowchart that we made, and that formidable flowchart is made into these 4 different things. One is phenology that I said we'll do in probably 3rd lecture. And as you can see, I won't be able to go through details, but I'll be able to tell you what to do, what to read, and how to think about it. This is a phenology, as you can see, is the Brownian motion, Fokker-Planck, and all this stuff. And sometimes I put hydrodynamics into these, but here what I have done, I have set hydrodynamics separately, and I put that with the, because fundamental approaches That is Liouville equation. Now, Liouville equation essentially was then gave rise to kinetic theory of gases. That's what Boltzmann kinetic equation. And then Enskog, and then that was this is the exact. There's a very interesting thing about the two. Hydrodynamics gives you time correlation functions, but does not give you transport properties. But the microscopic approach, kinetic theory of gases, give you the transport properties. Like you need viscosity in hydrodynamics, but hydrodynamics doesn't tell you how to calculate viscosity. Viscosity is calculated by kinetic theory of gases and the development thereof, going over into a time correlation function, which we talk about. They have all been combined together into mode coupling theory, and this development continuing, now aided very much by computer simulations. So that's on the last column. So we will be mostly these first three columns in a very, very simple way. But as I said, there are a lot of requirement. But this is the landscape that one talks about, one hears about, and one. And of that, I note very important thing is the time correlation function, which basically came first from the time correlation function formalism that came. That is the one that Rayleigh spectra. So that hydrodynamics gave rise. We should not forget history at all. And I'll talk of hydrodynamics a little bit. And Liouville equation, on the other hand, I said, is the desire to understand the transport property, calculate the transport properties like viscosity, like the even the pressure on the wall that came out from Maxwell Boltzmann. And so now I have quickly go through what is between relation between theory and experiments. And one little story. Let me tell you that I was reading. I think Sravon sent me a small piece of Wigner on Einstein and why Einstein was so creative and why Einstein could do what so much he could do. One interesting thing, Wigner said that Einstein used to take tremendous pleasure in what in doing science. I am writing a blog on that, which will be published in a few days, but you can, I elaborated on that a bit more. But one thing, important thing is that these people are always kind of connected with experiment very closely. And in time-dependent statistical mechanics, this is a slide I have shown before, that these are the kind of experiments I already talked about a little bit in one slide before, that these are the time, but here I talk of the time scales. Time scales that from femtosecond, which is not too much chemistry, but at one time we said the same thing of femtosecond. Before his death, Ahmed Zuhail was doing femtosecond in order to do electron diffraction to see how a bond breaks. Now femtosecond, picosecond, nanosecond, microsecond, all the way. So I just have a very few here, the kind of things that we are dealing with time scales. So these experimental methods and techniques, or this probing of the experimental phenomena, gives us the information and the motivation and the guidance to develop the time-dependent statistical mechanics. You should never think away from experiment. Okay, so again, experiment going on, the different length scale, different time scale, then time domain and frequency domain. You have experiments on structure equilibrium, you have experiments on dynamics, you have single molecule, you have collective, you have huge number. And there is one, this slide you can find out in this a Viewpoint article written a few years ago, that what is the, that's why there was the different experimental techniques that we, PHL, yes, protein hydration layer. That was one of the reasons, because there are some controversy going on. We have settled the controversy. It required some work and not a very difficult work. People, when they want to be confused, they will be confused. And that I think you cannot do much. But so there are a huge number of experiments, NMR, NOE, MRD, QNAs, neutron scattering, actually, dielectric spectroscopy. So this huge number of experiments giving huge number of data, and they are probing. But unless you have a theory, like happened in the case of protein hydration there, unless you have a theory, it can be all very muddy, can be very confusing. So the job of StatMech is actually to understand these experiments and kind of separate oranges and apples and try to get a coherent picture. picture, a quantitative picture, is the ultimate goal. So then I again say, continuing with experiment and that there is time domain. I have just given what very simple the time driven process, Stokes shift, depolation, all the laser experiments now that is time domain. Actually, that made huge amount of impact from 1980s, and of course very old classical frequency domain, which we didn't quite understand until and unless the time domain was developed. So these are the things. We have time, we have frequency, we have length scale, we have the momentum, wave number. So early days we had frequency and wave number because they allowed us to exchange energy and momentum with the system. So by exchanging energy, how much energy is getting absorbed or released and momentum getting scattered, we could get the information. That was the early stages. Now we can of course do excite directly and prove. That's the time. So the way to think about frequency and wave number domain is that they are the perturbations. So again, now this is a very important slide. And this is a slide which has a huge amount of information in it. And I have in my book, I'll describe a little bit more. How does we do that? How does we connect theory to experiment? Where is the statistical mechanics coming in? And how does it fit in? So, for example, you want to do neutron scattering or light scattering. Let's say light scattering. The derivation is given in Biman and Bagchi, I think, chapter 2. There, they set out to derive, and they derive, and that comes from actually classical electromagnetic theory. That light, is the electromagnetic wave that comes and interacts, and you get the exchange of energy and momentum, as I was saying. Now, how much it is absorbed and how much is scattered, that you can measure. So now you need to have a for scattering cross-section. Now, why does scattering takes place? Scattering takes place because of fluctuations, the density fluctuations. The liquid, many regions, if you consider the liquid into small little bits of having 1,000 molecules in each bit, each grid. And then the fluctuations are those fluctuations which are making density different in each grid. Somewhat longer wavelength, because we are talking about hydrodynamics, where the length scale is say 5,000 angstrom. So there are many more water molecules, million water molecules, so more. Now the density fluctuations are giving, because of density fluctuations, each region has little different density, and as each has little different density, is a different refractive index. And we know from our high school physics that if you have a different refractive index, then light get refracted. It bends, and that's a scattering from the in the long wavelength. So now in Biman and Bagchi, you've given that what is the cross section, scattering cross section sigma. The same thing goes over to neutron scattering. So the differential scattering cross section, which is by slightly moving the solid angle and the momentum, what do we get? Is we get what is called the dynamic structure. So the relations, so this from electromagnetic theory to go to dynamic structure factor goes through classical electromagnetic theory, and you need to do, in the modern days, you do the derivation through Fermi-Golden rule, which is a scattering from one wave number to another wave number. So you have to derive first, what is that you are measuring? Okay, by light scattering, this is this scattering cross section. What is it from? Well, diffraction. How do I get it? Because there are a bunch of transition. Who gives me rate of transition? That's Fermi-Golden rule. Okay. Now, after you do the Fermi-Golden rule, you get ultimately what you want. You want an expression in terms of time correlation function. That's why 90% of time in StatMech works. But before that, there are all these other things. That means there are all the different kind of theories going on to bring you to time correlation function. There people are calculating diffusion, conductivity, and all these things. Okay. So, as I was saying, that what essentially gives rise to a scattering or all the observables are the fluctuations. Though these are the fluctuation in energy, I think Shomok sometime prepared for the book. And these fluctuations are the ones which are extremely important. And why? As I said, I'm going to talk of the course very much in terms of physical picture and develop that physical picture and then correlate it and connect it to what we do quantitatively, which in terms of computer simulation or analytical theory, time correlation, function level equation, all these things. But underlying, there's a beautiful and very rich, elegant physical picture that you must understand. Okay, so as I said, you this left-hand side of the equation is light scattering, and the right-hand side is the dynamic structure. This is the expression, and K is K2 minus K1, coming and going, and all this exchange of momentum. Now, the dynamic structure factor is the Fourier transform of the density time correlation function, Fourier transform density. So, see, when does theory? You see, when we first started doing theory, the wave number dependent, everybody talks of density. We are very confused. Why do you have to talk of wave number dependent density? What is that? But that's because that's what experiment measure. So the condensed matter people, physics and chemistry were correctly emphasizing on these things, but it's not very clear why we have to consider and calculate these quantities. Okay, so this is the reliability spectra. So dynamic structure factor by light scattering, what is last equation here within the box, is this quantity. When you do the light scattering, this is even now enormously used, this technique, reliability spectra. There are now very, very powerful reliability spectrometer. There are 4 or 5 in the world. One of them is actually in JNC. As I'm told that each of them is some kind of $5 million or some kind of equipment, but they allow you to do low frequency, high frequency, scan frequency, and wave number. It has 3 peaks. Central peak is the famous relay peak, also called the heat mode. DT is the thermal diffusivity. And other 2 are sound mode or acoustic. They are below a peak. They are displaced by sound velocity. But the reason I am spending a little time on that, I'm very fond of this spectrum, because that spectrum is one of the few things that gives you so much information. They give you thermal diffusivity, they give you a velocity of light, and the width of the below peak is the sound attenuation coefficient gamma. Sound attenuation coefficient is a combination of shear and bulk viscosity, and this is one of the very few places you get the bulk viscosity. Shear viscosity you can get through a viscosimeter, but not bulk viscosity. So one experiment, so many beautiful things and fundamental things coming out. That's why reliability spectra is so important. So I want to make one point here, that this is how experiment and theory come together. Reliability generated these things. And so immediately experimentalists had the reliability spectra. They knew that width of the central peak is the thermal diffusivity displaced by sound, below peak displaced by sound velocity. So this is one of the is a fantastic example of the relation between theory and experiment. Now there are many more relationships, like what is I think it is chapter 3 in our book. That is in infrared spectroscopy, and that is, many times chemists take the infrared IR spectrum, but then to them it's the position of a bond, but not the position of the bond, it's the width and many things. Even the displacement of the bond tells you a lot of things. So this is another time correlation function. That is the UI and UT is the dipole moment vector most along the bond, and these are the QI Q0 is the displacement. Now in isotropic Raman scattering, you can show it is just the displacement vector, normal coordinate UI0 QT. This is beautiful, and alpha is the polarization. That's a beautiful relation that is again very widely used, this experiment. So people are measuring these things. But unless these experiments came, we could not connect the experimental results to what is the underlying microscopic quantity. So now a few basics. Going through that, the statistical mechanics offers methods to convert microscopic information, microscopic observables. That is this already I talked about this. So continuing that, we did on the some giants. No one is Maxwell, Boltzmann, and Willard Gibbs. I'm spending a lot of time with Boltzmann these days. This is H theorem and many other things. So Boltzmann is regarded as the father of statistical mechanics for many reasons. One of them is the entropy formula SKBL and omega, which is the beginning of, that's what Gibbs used to construct the ensemble picture, because that's a microcanonical ensemble. Okay. Now, according to William Mulligan, that's a beautiful, beautiful quotation. I always like it. Mulligan, in pure science, Gibbs did for statistical mechanics and for thermodynamics what Laplace did for celestial mechanics. Laplace did many, many, many other things. Okay. Like he is the father of central limit theorem of probability. Okay, did for celestial mechanics, and Maxwell did for electrodynamics, namely made his field a well-nigh finished theoretical structure. Now, what we need now in these two postulates of statistical mechanics, one is time average equal to ensemble average, and equal a priori probability, that is things. Now, then the two postulates are connected together by ergodic hypothesis. It's very, very important. You know, ergodic hypothesis was introduced. That's one thing one has to remember. Despite the elegance, beauty, and sophistication, statistical mechanics is an extremely practical subject. You know, it allows you to calculate. It's to me, it's just, we are kind of carpenter, you know, with a certain set of tools, and the tools are given by statistical mechanics. So this is a time average and ensemble average. I'm not going to spend time on that. It's in detail in my stat map book, because if I start talking about it, that go. Time-dependent StatMech is, along with Maxwell and Boltzmann more than Maxwell. First thing is the kind of theory of gases, but that he was inspiration of Maxwell. Then, of course, this how many things that Einstein did is just amazing in statistical mechanics. The Brownian motion started the transport properties, or how to think of the picture of diffusion and random walk and Langevin equation. But one thing people don't talk about it is that Einstein also did the first theory of the fluctuation phenomenon. That is in Landau-Lewis' chapter on fluctuation phenomenon. He said, what is the probability of fluctuation? He did it in terms of the work done. And then he expressed the work done in terms of the entropy, and then in that process, in the denominator, specific heat comes, and delta E squared C comes. Okay, it's just amazing. That's what I said. The connectivity in time-dependent StatMech with equilibrium is that. So when Einstein did dynamics as a not Brownian motion, the other paper is 2007 paper I'm talking about. That's just a wonderful paper, you know, just. But if you don't get the hold of the paper, it's Landau-Lewis. Landau-Lewis is just a wonderful book. You know, it preserves the beauty of the paper. Okay, now now what here is this equilibrium, thermodynamic response function are fluctuations of energy, fluctuations of dielectric constant, moment, which is dielectric constant, fluctuation of density, which is isothermal compressibility. These are all equilibrium fluctuations. Dynamics are where now we want time-dependent properties. These are, so standard deviations in this energy, dipole moment, density, they give you response function, standard deviations. The standard deviation is now replaced by time correlation function, like diffusion, velocity, time correlation function, like viscosity, transverse current fluctuation, time dependence, okay, frequency dependent dielectric constant, that is dipole moment, total dipole moment time correlation function. And I already showed you dynamic structure factor, density correlation. And actually, we'll see if we get to that it would be these quantities themselves are now replaced. The next step higher is these things are in terms of density time correlation function. Then once we know density time correlation function, we know that we are now talking of almost like radial distribution function. Then we can know that where we are here, intermolecular interactions coming. So the connection is very clear. Einstein is the standard deviation. That standard deviation delta E squared, that is given by delta E0, delta Et, and frequency dependent specificity. There has one very long paper by Shinji Saito and myself, how that is connected to thermal conductivity or thermal diffusivity. Okay. So continuing this, equilibrium response functions like specific heat provide a quantitative measure of the perturbation or displacement of the system of equilibrium. They provide the answer to the question, how much? But non-equilibrium response functions provide the measure of time and they tell you how fast. Beauty is that, and this is something actually I was telling Sumon, I guess, if I remember or somebody. Beauty is that both equilibrium and dynamic response function determined by the properties at equilibrium. They are evaluated at equilibrium. The explanation comes from linear response theory, and which we'll certainly do, most likely in the second lecture. And but it first appeared in the Onsager's regression hypothesis. So another landmark paper after Einstein's two papers are Onsager's regression hypothesis that we'll do today, if time permits. Okay. How to think about it now? Think of a drop of ink in a beaker or an open iodine bottle. My example in the class, that in water beaker, I drop a ink and initially I can see it, then it disappears. Or I open an iodine bottle in a corner of a room and I can see the iodine molecules, then I don't see it. Where do they go? They diffuse away. System, inhomogeneous system becomes homogeneous. So density delta function are highly localized in a short time at the middle panel showing how it diffuses. And many experiments we do are we displace it from, like you can take a pendulum and aid. So system is very much like a pendulum. And a system that we study are held together by certain springs. Those springs are specific heat, dielectric constant, evaporization. So we displace the system and the springs bring it back. Now springs bring it back requires two things. It requires the spring constant, but it also requires the dynamics. And so that's what I said. How much is displacement? That equilibrium StatMac will give me my T equal to 0. But this approach to equilibrium that I am showing here, the approach to equilibrium, and that is my non-equilibrium statistical mechanics. So one more that is very standard we do in spectroscopy. We are exciting ground state to higher state population, and then we are relaxing on the harmonic well. So it is the same as what I have said here. So these are the experiments we do in all relaxation experiments, all from force and transfer to vibration, relaxation, solvation dynamics, electron transfer reactions. This is the kind of things we do. That's actually Rudy Marcus theory. A little bit of that we'll just touch upon. Okay, so now, but how to describe these things? See, they are not one point, and they are, as I said, that they are not deterministic. There is a macroscopic systems, and they are changing by macroscopic amount. And however, time scales are often not microscopic. They could be macroscopic, but so how do you go about it now? So as I said, it starts with probability, and that's why Boltzmann was so much criticized, because he introduced probabilistic concepts into statistical mechanics. He was tremendously criticized. But I read reading many of Boltzmann's book on the papers now, and two papers. I feel like criticizing him all over again, because they're so difficult papers, nice papers, all right, but I think half of the people who criticized him didn't understand what he did. Okay, so now we'll go through a few things for students, which is my course in probability theory with the concept of random variables, sample space, joint probability, distribution, and all these things, conditional probability. So these are the things will be quickly done in 5 minutes, and I give name of the books. My favorite book all the time that I studied is Failure Probability Theory Volume 1. Just amazing books. I remember I had Failure 1, I had 2. One is though there was ELBS, English language, some program, very cheap books we used to get. First one I bought hardbound, paying some $40–50. Next one I paid 20 rupees. Then the Kailai Chung, this was the course on my undergraduate senior math level probability I took. There's a wonderful book, Kai Chung is known as KLC, KLC1 and KLC2. I am recommending you KLC1. Failure, I am recommending both for one. And Harman Hacken, Synergetics and Introduction. These three books, please. These days, as far as I understand, and I hope I will not be taken to court, that people have easy access to books. But please get these books. Okay. Now, I'll again go through that samples, basic idea. This you have done in class 11 or class 12, that what is the sample space. So why need a sample space? Because probability distribution is defined on a sample space. Sample space is a collection of all outcomes. Like if I have a coin, I toss it twice. Then my sample, what are the possible outcomes? That is a sample space. It is HH, HT, EH, TT. If I have a die and I roll it 3 times, then I have an order matters. If I make the order matter, then is a permutation. I have this like 1, 1, 1, 2, 2, 2, 3, 3, 3. This I have only 3 times. Okay. Then I have 1, 1, 2, 1, 2, 1. Then I have 1, 6, 1, 5, and all these things. Okay. Order importance of permutation. Huge number. Just you see, just in dice in rolling 3 times, I have a very large number. However, many times, we have something which is continuous. So let me summarize first before leaving this space that I define a sample space, a collection of all possible outcomes. Okay. So it is again I'm repeating that characterize, and there's a reason I'm repeating that is obtain information about the elementary events and construct probability of a given value. So once I know the measure or the volume of the mathematics language is measured, I don't want to do any other language there, of the sample space, then I can define a probability distribution, which is, you can say, an area of a given space in a multidimensional space. So one thing that comes to your mind immediately, if you know any a bit of statistical mechanics, then is the phase space. And all our work is on phase space, configuration space or momentum space or full phase space, whether it is single molecule or particle phase space or in particle, there is new space or gamma space, which is full in particle gamma space. This is where we define our probability distributions. This is where we define our dynamics and our equilibrium statistical mechanics. So once we have the sample space, I can define probability. So till now, what I have done, I have said I have defined, I have assumed a random variable. All its possible outcomes is the sample space, and the probability of having head in my previous example is 1 by 4. So that allows me to get the probability without knowing anything in unbiased coins. Similarly, dice, I can get the probability. So so sample space allows me to define a probability function. Okay, this is the take home with these 2 slides. Now, if I have a continuous variable, then probability outcome we talk of between x and x plus dx, and that is px dx. If I normalize it, then px dx integration is 1. In the case of random variables are time dependent, that's very important. And what important thing is that in equilibrium stat math, you can take many measurements. You don't have to worry about time. But non-equilibrium stat math, when you take the measurements, the interval is important. So it is, we need to, so I make measurement 1 and measurement 2. As if I throw the dice, after 1 second or 2 second, results vary or become different. That doesn't happen. We know that, and I'll come to that. So the interval, so time dependent stat math, we talk about interval, and that interval is the time. Okay, so thus word distribution is time dependent. Now, this is a very interesting thing that, see, when we talk of measure the transport properties of time dependent time collision functions, we do that at equilibrium. Why do we want to do those things in equilibrium? The simple answer is that all the figures that I've shown relaxes to by state using processes which are essentially unaltered from the equilibrium state. That means we get information about the rate of relaxation by studying properties at equilibrium. This is one of the most important achievements of time-dependent statistical mechanics. And this is what is Onsager's regression hypothesis. Little bit in, if you see, Onsager wrote a series of papers with Onsager much love. Even this, his 1931-32 paper, submitted 31, I think came out 32. These are all the same thing. This is the regression hypothesis that we study equilibrium processes, but by studying equilibrium processes, we talk about non-equilibrium. And this is, I'll be talking a little bit more about it. And this is then, for example, I have a density, as I said, the ink spreading. What is the functional form? Functional form is Gaussian. But interesting thing here, note that this rate of spread is given by diffusion D, and diffusion D is measured at. So a non-equilibrium process is measured at equilibrium. This is a very interesting thing to remember, because I'll come back to it again and again. Next, what we need to know about joint probability distribution, that two events together, for example, a particle at position R, the particle that was at origin at time t equal to 0 goes to a place delta R after time t. So that would be joint probability distribution, position at time. So joint probability distribution is the measure of correlation, as we'll come to that in a minute. So I need joint probability distribution like radial distribution function. These are all joint probability distribution. So you must understand the joint probability distribution, and if they are independent, uncorrelated, like radial distribution function, remember at R going to infinity, GR goes to 1. GR goes to 1 because two particles becomes uncorrelated. So joint probability distribution becomes a product. And remember in GR, the definition is that probability of a particle at one particle at one R1 and the R2. But then you divide it by rho R1 what. So in R1 minus R2, the space is long, then they are not connected. So they become, then say, if two variables A and B are independent, then joint probability distribution is product of these. You have, I just reminding you, most likely you have studied quite a bit in your school or undergraduates. Now comes a very important quantity, which is the conditional probability. This conditional probability is defined here. Conditional probability is that given one, B has happened. What is the probability of A? I might have screwed it up. It's AB here. So given B, yes, A, what is happening? Now, conditional probability is essentially your time condition function in dynamics. And conditional probability, as I already said, your radial distribution function. So when people developed these things in 1930s and 40s, the radial distribution function, time condition function, they already, whole probability theory has been completely developed. So the people who did it, like Johann, Born, and Karkut, they fully had the advantage of the probability theory. And so probability theory really very useful to understand these things, where it came from, and more importantly, to give you a physical picture of this. I am not doing a great job. This is, I have a chapter which is far more detailed on probability theory, and which we'll do in, we'll use it several times in the course of this course, and you will. But I recommend you that you get Feller and Kyle and read little bit. You will, those of you who are serious, you can get tremendous benefit, particularly because, see, what Feynman used to always tell, that why, he asked him why you could do so much, because he was very talkative. His standard answer was that I could go further than others because I had a different set of tools. And what are the different set of tools he made? It's very interesting. He said one of the tools that he again and again mentioned, he knew how to differentiate under the integral sign. I found that very interesting, because by that time I was taking that course in advanced applied math, and we are taught to do the other techniques, presumably very popular in 1890s. Then people forgot. Feynman actually elaborated on that, how he came to do it. When he was in school, two things happened. In physics class, he was bored. because the teacher was teaching some classical mechanics or something, optics, whatever. He was completely bored. And then after this class ends, everybody is going out. The teacher said, Feynman, that you wait. And then he taught him principle of least action. And Feynman was absolutely thrilled. And principle of least action went on to become path integral formulation of Feynman. And in mathematics class also, he knew all these things. So they was bored. Then the teacher told him, I'll give you something very interesting and you like it. And gave him 1890. That kind of remind me our trigonometry Loni that was very popular in Calcutta, we used to do. But that book had these forgotten techniques of calculus. And he found that. So Feynman always said his success is because he has a different set of tools. And it's very important that and Zwanzig had a 2-page article typical of it where he says a serious student must learn as many techniques as one. So probability theory, I very strongly recommend. And if 170 or whatever is listening to it, if 2 of you go and take a book of probability theory and read, I think I'll be successful.
Okay. Sir, before you go to next slide, there is a question from Harsh. He asked that what is that semicolon in the previous slide, in slide 33, the equation in the bottom, this semicolon, r comma t, then semicolon.
Oh, no, but you don't have to have a semicolon. It just means that it was at a time, there's a joint power distribution. It could have been comma, but I have already used a many comma. So, what is the joint power distribution? That a particle at time 0 at r0 is later at time t found at r. That's all. It's a joint power distribution. Okay. Now I go into 2 extremely important things, the things that I use even today. One is the central limit theorem, which is in my every book, my equivalent stat mac book or my non-equivalent stat book, I always talk of central limit theorem, CLT. Central limit theorem is a wonderful. When I first read it, I didn't quite believe it. But this is how your random number generator is created. Your Gaussian distribution is created. If I have n number of random variables, like calling a random number generator, and I add them up, and the sum I call it capital S, then central limit theorem said that the capital S is a Gaussian distribution. It's just unbelievable. It is exact. It is absolutely beautiful, done by Laplace, and then also done by, explained on that by Gauss. And that explains to you why energy is a beautiful Gaussian, the energy of a liquid, moment fluctuations are Gaussian. All these explanations, microscopic explanations of them. So Xi, what are the conditions of Xi? Xi is to be independent, but it is relaxed later. It doesn't have to be fully independent. They can be weakly correlated. And then you can define very rigorously what is the weakly correlation means, which our energy fluctuation, moment fluctuation satisfy all that. So, but look at the beauty that if I can consider a property, sum of random independent variables, which energy and many other things, as I said, are, then that sum is Gaussian distributed. I think I know of probably no other theorem which is so useful, so practical at the same time, so beautiful. Next thing is that another great theorem. These 2 theorems are the greatest of probability theory. Let me tell you that. One is Dup's theorem. This is now widely used in Markov process, Markov chain, and all these things, many other things. If a random process is a Gaussian distribution, which is central limit theorem, and if it is Markovian means it depends only on the previous, but not before that. So it has no memory or very limited memory. If a random process is Markovian and has Gaussian distribution, that random, that means that distribution is independent, time independent distribution is Gaussian. Then the time correlation function is exponential. Isn't it just a beauty? This explains why velocity time correlation function is Gaussian in gas phase and not Gaussian in liquid and solid. And I've written it twice. So Doope's theorem tells you about the time to decay of the time collision function. So these two together tremendously helps understanding of equilibrium and time-dependent statistical mechanics. Okay, now I come to more formal and a little bit difficult things. One is so I have done relation preliminary, I have done relation theory and experiment, I have done probability theory. So I have done 3 chapters of my book. And now I'm going to do the 4th chapter of my book, which is more serious and that is the relation between that where the transport properties enter statistical mechanics, and which is the beginning of the formal statistical mechanics. But no, formal statistical mechanics was done by Boltzmann and Einstein, more by Boltzmann. But this is, in the work essentially of Onsager, which connected, which kind of ushered in many important concepts as I discussed. So if I have a force like X and I have flux, then force and flux are linearly related. So this linear relation between flux and force, or the flux is the movement, the transport property, the flow of matter, rate of flow of matter, the rate of number of particles flowing through a unit area per unit time. That's flux. And the flux is related to force. And what is the force? Is the interesting thing is that here we are almost thermodynamics. The force is a collective force. Like, yeah, I know that if there is a one place is more concentration than the other, then it flows from the high concentration, low concentration, high temperature to low temperature. Though the force is dc dx or dt dx, and proportionality constant, which is my L, is the are the transport properties. This is really beauty. D is the self-diffusion coefficient, lambda is the thermal conductivity. So that is where just like you consider it almost like that in specific heat. You give a temperature, you give a heat, temperature goes up, and specific heat is U by T. Here also on the Nimsha. Ashwara, I'm teaching a course. I'll talk to you later. Okay. Thank you for the picture you sent. Okay. So, so this is try to understand it in the same ballpark as the group of stat. And please ask if you have any question, because they are just too beautiful. What did Onsager did that is credited so much as one of the fathers of time-dependent stat mech? He said, okay, so long we have been talking of one perturbation. Now let me consider 2 perturbations. Onsager was really a guy who did enormous thing, but without time collision functions. This is very important to understand that Onsager did what he did could have done much easier if he had time collision function. He didn't have. He was doing 1930s. Time collision came into being in mid-50s by Green and Kubo. Okay, 2 perturbations of the system. They can be temperature gradient and electric field, or then temperature and electric field. Then temperature gradient gives rise to flow, just as heat flow. Electric field gives rise to current flow, electric current. So I have these 2. But Onsager said there are one more that we all know. If you have gone to museum, like our Visvesvaraya Museum here, they have this experiment that if you put your, there's one part is cold, metal, copper, other one is metal, you put your hand on, temperature gradient sets up, you see the current starts flowing. So temperature gradient gives this current, and current gradient gives rise to heat. So these are cross correlations. Onsager proved that these here we have L11, which can be D and lambda, L22, but there is L12 and L21. And these L1 to L21 are equal. Today, in terms of time correlation functions, I can simply prove, but for those days, it was not easy at all. But was he given a Nobel Prize or so much respect because of just a reciprocal relation? No. His real thing, just a second. Now, I think I have to go to my, this where I have become lazy. So I will now share my force and flux if I can. Okay, you can see, na? Hello?
Yes, we can see. Yeah.
Okay. So now, okay, so this is the two things that you probably know, Seebeck effect and Peltier effect. These are the two things I was talking about. That how can electricity, different metals can do that. Now, Onsager's regression hypothesis, this is the figure I wanted. And I should have probably cut and paste, but okay. So, why I hold such huge value to, just a minute, let me get it in one page. Okay. So Onsager's regression hypothesis tells that this is the birth of linear response, or beginning of linear response. That I have this surface. I told you that our system is nothing. Our system is nothing held together by a bunch of, somebody has to turn off, somebody has to mute. Somebody has to mute.
In the same slide, nothing is visible. You have to display something else.
It is not visible.
No, sir, we cannot see equations.
Equation, I am not saying. Picture?
No, nothing. No text, nothing.
So
Too bad.
You are still at the PowerPoint slide.
That is very bad. So I'm going to now do something about it. So I have to stop sharing, and I think coming, but that will be a little bit painful. Okay.
If you share your whole desktop, then we can see both the files.
But how do I share my whole desktop?
So the first option, that desktop one, when you share, choose the share option.
Let me see. I can, if this works. Share screen. Okay.
First option is desktop, I think.
Now you can see, na?
Yes.
Okay. But I probably will not do too much. So the regression hypothesis is the where I told you the system is actually held together by a bunch of springs. That's why you have a polarization 0. That's why you have average volume or average density or whatever. Now, Onsager's regression hypothesis is the following. I disturb the system from equilibrium. It now relaxes back. So the time dependence of the relaxation from this disturbed equilibrium is given by the same way the fluctuations decay. Okay. So that is the regression hypothesis. I think I have, yeah. So if I define a function, which is these time correlation functions, which are fluctuations, microscopic quantities. And that is then, and I define another function gt, which is the macroscopic. So equation 4.7 is microscopic and 4.8 is macroscopic. Onsager said that these two are the same. That means that is the regression hypothesis, that your time scale of macroscopic perturbation or fluctuation going back. This is what I talked about, is that the specific heat, which is a property at equilibrium, gives you the rise of temperature when you give a heat to it, and to a satisfactory degree, to a reasonably good amount of displacement. So Onsager regression hypothesis is the beginning of the what we call the linear response theory. Okay, now there now remains some very, very important steps that I probably will not do fully, is that derivation of Onsager's reciprocal relation. And that is uses the entropic things, and actually this is where I was saying that this equation 4.10 was actually done. It was in according to Landau-Lipschitz, Einstein's 1907 paper. So this is what the beginning of this is the irreversible thermodynamics in its full glory, and then this proof, which is not a very difficult proof, and I can give this proof. You see, this book is still in the making and corrections and all these things, but I can send this to whoever want, but please wait for a little while, because after the second lecture, I'll send the chapters to you, the proof that the LIK equal LKI. But the important thing is that, as I said, Onsager at his time didn't have the time correlation functions. So proof heat was really far more difficult. You can make it far more easier by doing now, irreversible thermodynamics, I'll not go into that. But then goes into the rate of entropy productions and Pigozin's theorem that the production of entropy is minimum. That is also an important thing. But this rate of entropy production as such right now in our, if I get time, I'll revisit it is done quite well in the book in this chapter. That but if I do it, I'll come back in later in the chapter, where we do irreversible thermodynamics. Right now, I'll stop here. These ports are flux, and I want to go on to talk about my next chapter, which is hydrodynamics. So I'll stop and share again. Just bear with me for a minute. Okay, so now I'll go and but hydrodynamics, we have to again do the same thing, So okay. So I already told that what are the things? Again, reminding you of the sequence of events, sequence the way it is going. I started with the preliminaries, that saying that, okay, why do we need to study time-dependent statistical mechanics? What does it give? I have a bunch of slides to tell you that this is why we did that. Then we have relation between theory and experiment. There I talked of the reliability aspect. And I talked that reliability aspect is not, in the context of that, the Fourier transform of the density time correlation function that you measured by light scattering. And I told you that the reliability aspect gives you huge amount of information. Now, how do you derive reliability aspect? How do you get the very first time the density correlation function was calculated? It was interesting that density correlation function was done. Time correlation function actually appeared. Hello, can you listen here? Hello?
Yeah, sir, please go ahead. I had to mute somebody else. Yeah.
Okay. Yeah. So this is nothing. I gave a talk somewhere. They had hybrid, and the hybrid mode. Somebody was, I think it was Tripura University or somewhere, and the hybrid mode. Somebody was talking at the asking question and saying something top of the voice, which I couldn't hear anything at all, because they didn't have a mic or something. And it went on for quite some time, and there is no way you could mute anybody, right? Because this was a hybrid. So hybrid has this thing that you have to have individual mics or something. Otherwise, hybrid is a very, very difficult proposition. Okay, coming to hydrodynamics. So hydrodynamics again, and this is for students, that we build it from a conservation laws. And I will have the 2-3 pages. I don't think I have slides on that. Okay. No. Okay. So the conservation laws of the number, density, momentum, and energy. Then conservation laws to be supplemented by constitutive relations, which are essentially like this Fick's law and Fourier law. But it is now at the level of the momentum. That's an Navier-Stokes equation. And then you can, under certain approximation, you can solve them. And I'm not going to do the whole thing, but as I said in the chapter, which I can send, we have shown how to solve it. It is in many places, and I recommend the Born and Pecora. Only problem here and there in these books, I found some places there are a little bit of problems, like they did not clarify the things like why they are making local equilibrium approximations and what are the limitations. All these things had not been made clear, but that's fine. So that one can solve for the density relaxation, and that leads to reliability spectroscopy. And in that chapter, I have also given a derivation, or rather some part of derivation of the Stokes relation between friction and viscosity that we use all the time. So, as I told you, that hydrodynamics does not give us transport properties that come from kinetic theory of gases, but hydrodynamics gives you essentially, in all practicality, the first time correlation function that came from hydrodynamics, and then that is the reliability spectrum. But it gives you relation between friction and viscosity. That means it allows you to calculate the force, and that's the Stokes relation. That I have a force and I have a constant velocity. The proportional constant is again a linear response. This is very important, and I'm really emphasizing it in the book, that one of the first appearance of linear response is the Stokes relation. That is the force. I am applying a force, but you see, Newton tells us if I have a force, then it should accelerate. But when I pull a ball with a certain pull a ball by string, then it moves at constant velocity. That constant and the proportionality is the friction, and so that one can derive that friction depends on the viscosity, and this relation between friction and viscosity, that derivation is really very nice derivation that solving hydrodynamic equation, but they are pretty simple. It is given in usually not given. Landau did not give it, but there is a book I like, is Horace Lamb. Horace Lamb, in the appendix of the Horace Lamb, there's a very nice derivation of the Stokes relation. This zeta equal to 6 pi eta r is given. Okay, so I will now do the little bit. So this is the perimeter of the hydrodynamics that we do in GET hydrodynamics. I'll do a little bit of kinetic theory of gas, and I'll come back to hydrodynamics, because then I have to change. And but with kinetic theory of gas, today's lecture will end, which is almost an hour. So kinetic theory of gas, which is you should remember that that's why transport properties first came. That is the Maxwell-Boltzmann who derived the expression of viscosity, and then this in terms of mean free path, then thermal conductivity, diffusion constant. So viscosity and thermal conductivity expressions came from kinetic theory of gas. And there's a very interesting assumption there that they don't interact but they colloid. Okay, that's very, very interesting. I always find that it's ideal gas, they don't cohere, but then Maxwell very active, and Boltzmann has very nice. Boltzmann of course did many other things. Okay, now the Boltzmann, Maxwell's initial paper was moved Boltzmann so much. I have a book presented to me on Ludwig Boltzmann by of no other than Professor P. Ramarao. Very interesting. This Boltzmann kinetic equation is Boltzmann was so impressed by Maxwell's paper that he carried that paper all his life, and then he tried to extend it to take interaction into account, and in the process he derived his Boltzmann kinetic equation. In the process, it is Boltzmann H theorem. In the process, is this molecular chaos. In the process, is the Boltzmann's formula. And then people like Chapman, Cowling, and Enskop derived Navier-Stokes equations from Boltzmann kinetic equation, and then latest in the ring terms and the correlated collisions. Because all the way up to Navier-Stokes was a binary collision approximation. So kinetic theory of gas is just beautiful, if you take its totality. So this, I remember I showed that there are these two pillars of time-dependent stat mech. One is hydrodynamics and this kinetic theory of gases. And they go really, and then they were merged together. They come together to form the mode coupling theory. Kinetic theory of gases give you the transport properties, And hydrodynamics is given to you, maybe a Stokes equation, and all from that give you the time correlation function. Now to calculate the transfer properties, so time correlation function formalism came by Green-Kubo, the integrals, then of course the marriage becomes clear that I have now a method to calculate the time correlation functions, and I have an expression in terms of time correlation function. So, and that's what hydrodynamics were extended by with the help of Biman to molecular hydrodynamics, and kinetic theory of gases were developed by many people, Dorfman, Cohen, D. Schaeffer, and many other people. And these two were combined together had to be combined together, because in order to get the transfer properties, I need the time correlation functions, and that input came from hydrodynamics. I think this is already 1 hour. I think students will be bored. So what we will do, Shumon, in about, because there are a lot of students who joined today. At one time, I was saying 180.
Yeah.
So now, what we'll do, I will in between have about 3 weeks or so time, another half an hour or 40 minutes. Let me talk on hydrodynamics and kinetic theory of gases and the interconnections.
Sure.
And after that, I'll start the fundamentals and formalism, which will be Liouville equation, time correlation function, position operated technique, moments and cumulants. If we can do that, then we'll do the third part, which will be, I'll stop there because I'll not go to applications. That is the phenomenology. That's where I want to random walk. I want to do Langevin equation, Brownian motion, Fokker-Planck equation, things like, and that will be a lot of fun. Though a lot of equations will be there, but it's a lot of fun. So, but I think it is too late to do Navier-Stokes equation. Kinetic theory of gas probably a little easier to do Boltzmann kinetic equation. But hydrodynamics, I believe majority of our people are from physical chemistry or a. So we'll decide, and please join back in a few weeks' time. We'll announce, as Shumon does a wonderful job on reminding everybody. We'll do hydrodynamics, maybe hydrodynamics, kinetic theory of gases, and kinetic theory of gases is easy for me to go to Liouville equation and BBA hierarchy. That would be, those three will be one lecture. Okay. So I think 4 lectures probably should be enough.
Yeah. Okay. Thank you, Professor Bagchi, for a very nice pedagogical presentation. We have learned a lot. So there are now it's time to take questions, probably, particularly from the students. So, sir, there were some questions in the chat box, and I think some equations are not clear to the students. So if you can go back to the slide 33, there students had difficulty.
I am finding something very interesting that I cannot make this thing. Okay, slide 33. Okay.
Yeah. So that equation, it seems some students are having problem.
I cannot see. Okay, I can now see. No, I cannot see. This is the one people have problem.
Yeah. So this below second equation, people are. I think you need to maybe explain once more the second equation. Yeah.
So we are talking of joint probability in terms of conditional probability. That's the relation. Okay, you know conditional probability is the radial distribution function. That means there is one particle at the center, and then what is the probability of other people? So you gave one. So this gives the relation between single particle, between joint. So P, left hand side in the last equation is the joint probability. Do you understand what is joint probability? The probability theory you probably would be.
Hello, sir.
Yes.
So, yeah, so I have asked the question. I'm Joita. So if the left hand side is the joint probability, then you have already discussed the joint probability equals to probability of happening A into probability of happening B if they are not independent. So maybe it is some conditional probability, and the right hand side is the joint probability. So can you please, I have a confusion. Can you please?
Okay, so the joint probability is I understand. I understand what has happened. Okay, let me rewrite this. I don't know that I'll be able to do it. Okay, now Oh, no. Okay.
I think it's an issue with the notation probably. That,
Yeah, that's all I'm
this
saying.
comma and bar.
Not the issue of the notation, not the issue of the notation. I wrote the equation, first line and second line are reversed. That's all. Not a notation. It's the way they are presented. So now on the left hand side, I hope now. I cannot do left hand side and right hand side now, but then I hope that I work. Just what? Okay. So right. So now you have to flip them. You flip them. That means, you know, PAB is the right hand top equation, right hand side. Right hand side of the top equation is the same as the left hand side of the bottom equation. So there is really no confusion.
So then this is the conditional probability distribution function, right?
See, when I have a bar, then that's a conditional probability.
Okay.
Whoever you are, I don't know, didn't get your name, please. This is a trivial thing. You got to read the books I said, though this is correct. But I don't have really the patience to explain this. But
okay, sir. Yeah, I
I'm
understand.
sorry, but you should get the Feller's book and get the Kailai Chung. Kailai Chung does a wonderful book. Well, at this level, you know, and this kind of course, the idea is to give you what you have to read. The idea is really not fully to teach. That is not possible. But I'll be able to tell you what you should do, how you should think about it, and how the flow of the subject, and in the process, some details. Now, this is correct, but if you have forgotten conditional probability, I don't know, is conditional probability taught in a class 12 or no? I know chemistry students don't learn conditional probability in undergraduate and MSc. That 100%. Okay. So because I know from my students, you know, they when they hear conditional probability for first time, they are very surprised that something like that exists. Okay. So anyway, please don't go to any other book. Don't go to Wikipedia or anything. Go to Kailai Chung. Kailai Chung does a great job because that's for essentially undergraduate fast probability course. Anything else?
Yeah, in the chat box, I don't see any other question. So anybody else, if you have any question, you can raise your hand. Maybe meanwhile, I'll ask something. It's fascinating that from the correlations in the equilibrium fluctuations, we get the non-equilibrium timescales. I was wondering that where it might break down. I would think that it should, I mean, it's surprising that it works so well. But in
the reason it works well, the reason I works well is that's why I gave the diagram, and I did not explicitly say it, but I have told many times that all the things we measure or the properties we perturb, the properties are held together by a set of springs. How do I know that? I know from the free energy extractions. Okay, like free energy of polarization, the famous Marcus is just the function of dielectric constant and then square of polarization. Same if you in density fluctuations or volume fluctuations. So the thing is that these spring constants are pretty large, and that's why the problem happens that when you go to critical phenomena, these spring constants go to zero, and that's where all these linear response, all these things suffer difficulties. But other than in the normal condition, the spring constant, the body or all these things, even in non-equilibrium, there are a lot of spring constants, and they are holding the system together. These spring constants are pretty, as I said, pretty large. Now, you can say large with respect to what? then you have to say, if I could, I don't have that, I should have put that here. Large with respect to the amount of energy I'm spending to displace it. So I displace it by amount, and then, so, and in that process, I spend this much energy. Since they are very large, much of the experiments or they do there, we are not perturbing it really from very far from equilibrium. You know, so we don't, this kind of logic doesn't work at all. For example, for active matter or other things, you know, where the spring is not there, or a new set of springs appear. And in that case, this logic doesn't work. So yes, the answer is that the springs are pretty big. They are macroscopic springs. We are talking about macroscopic perturbations. So that is the reason that even, you know, in the macroscopic field, see, something which is so funny. We use Fermi-Golden rule. In fact, now Boltzmann kinetic equation is derived. So, for example, Carson-Huang essentially by using the scattering from one momentum to another space by using Fermi-Golden rule. Now, Fermi-Golden rule is so microscopic, and we know that Fermi-Golden rule does not work. So, Fermi-Golden rule, if you do real spectroscopy, you know Fermi-Golden rule doesn't work there. But here it works so well. I have one philosophical answer to this, and this I think is true, is that it is, if you have something really, a truth, a kind of general truth, then you can arrive at the truth in many different ways. Like many paths lead to a big road, or many small rivers lead to a big river. So many different ways you can get to a more general truth. So these transport properties which work so well, the time correlation function formulation of the transport properties at equilibrium works so well. And so there is something really, which is same as what the question you are asking.
Yeah, it's very fascinating. Yeah. Okay, so is there any other question? Well, there is a question in the chat box. It's, I mean, I don't completely I mean, so if you are online, you can ask directly. I mean, if you can you can unmute yourself and ask. But I'll read the question. But let's see. Are we limited by mathematics to defining the reciprocal relations to no more than 2 state variables at a time? Or put another way, it is not much useful to understand the interactions of 3 or more state variables at a time.
No, we are not talking of interactions at all. We are talking of processes. That means we are talking of heat and current, for example. So they are processes, and those processes in the Onsager's picture, those processes are interacting with each other in the sense that heat can generate electricity and electricity can generate heat. So I don't know whether you mean by interaction. If you mean by interaction of the processes, I think people have done 3, as far as I remember, people have done 3 processes, you know, because this at one time was highly fashionable. Even now, I think a lot of people work on these things. Nothing, I think as of now, I cannot think of any reason not to have a relation L-I-J-K. So, but I have never studied those things, or I've never ventured into those things. So, if that is your question.
Yeah, he said it's that question, and he says, thank you, sir. Yeah, okay. I think it is answered. So I think that's all. And yeah, Shobanda has raised the hand. Shobanda, please go ahead.
Sorry, sir, the similar line with Suman, that you said that, you know, when the fluctuation distribution is a kind of Gaussian, then we always expect that time constant function as an exponential.
So that's not me. That Doob's theorem
looks to be. Is it?
Doob's.
Yeah.
Doob's theorem. Yeah.
Doob's theorem. Yeah. Doob's theorem. Yeah. Exactly. So now, if we really see any time constant function is deviating from the exponential, what do we really go back and see the fluctuation distribution then? Meaning, how to explain that part? Meaning, when you do see some kind of a system is behaving not like a time growth function, which is exponential purely.
This is a very stringent condition that first, many of the processes we study in physical chemistry are not Markovian.
Yes.
And, so this thing is not as general as central limit theorem, I'd say, but central limit theorem is time independent.
So the equilibrium fluctuations can still be non-exponential. Even we are looking at equilibrium fluctuations, but even at equilibrium there can be non-exponential
non-equilibrium fluctuations are studied, but that's far more complicated. Let's not get into that.
Yeah.
Equilibrium fluctuations, time correlation function. Now equilibrium fluctuations are the kind of thing increasingly we are studying in chemistry and biology. They are correlated, so they are not Markov process.
They are not. Yeah.
They are not Markov. They can still be Gaussian. That's what important thing. They can still be Gaussian, but they are not Markov.
I see.
Okay. Yeah. So yeah, you have any other questions, Shavandra? Okay.
Thank you.
Okay. So
sir,
and yeah.
Hello.
Anybody else?
Yeah. So if the process is Markovian, then the variables at different times are not totally independent. So how?
No, it is not Markovian. You are saying non-Markovian.
No, sorry. If the process is Markovian, if the process is Markovian, then it will be dependent upon the previous time step.
Right.
So then how will the central limit theorem change? Because for central limit theorem, all the random variables has to be independent or identically distributed.
Okay. You are taking the central limit theorem from the dynamics point of view. Okay, that's already kind of but say I have a variable, so central limit theorem I said is essentially for equilibrium. So, but and central limit theorem says that I think you are a little confused. It says the total sum is. Total sum is. That is a sum of many different things. It has many constituents. So, if I do, for example, energy time correlation function, and energy is a sum of, I can decompose into small parts. And then I can show energy is a Gauss. That's the first thing. Is it Markovian? Okay. But central limit theorem, much of the time the time is not anywhere. Okay. A is not anywhere.
Yeah. So I got it. There is a flaw, in the question. Yeah.
Okay. Actually, it is not a flaw because it is that at a given time, see, at a given time, I have say a number of molecules in the system, and a number of molecules in the system, and I take the velocity. Forget about Markovian process. So I look at the velocity. Now, velocity of each of these molecule in the system is a consequence of many collisions. So each of them, on the left hand side, the A's is at a time t. And so if I take a velocity of a molecule, it has undergone many collisions. And I don't need to consider this immediate collision. I can say, okay, it's enough for me to go to back 2 collisions because I don't have time dependent things. I have time independent things. Okay. Then I say become uncorrelated. That was this theorem is you don't have to be completely independent. You have to be weakly correlated. That is the basic condition. And that, of course, is a very mathematical domain, what defines weak correlations and all these things. And these are strong theorem, weak theorem, probability theory books. We'll have 2-3 chapters on that.
Yeah, sir.
Okay, so I think we can maybe stop here. So, and many students have asked for the recording, and I shared the link of our Google group and also our website. Please subscribe to our Google group, and as soon as the recording is processed and ready,
They usually go to spam.
Yeah, so I have taken another strategy. We are now putting direct registration link also in the website. So in case, just in case if you don't receive the link in time, just directly go to our website on the day of the talk and you should see the link there. We are not providing the link well in advance because there is again chance of spamming in the Zoom itself.
So to summarize, next lecture which Suman will announce is will be essentially, we'll talk hydrodynamics and we'll talk kinetic theory of gases, and we'll go to Liouville equation to pave the first finish of this part and start our journey towards the time correlation function formulation. And then things are a little dicey, position of it. I am now a bit suspicious and afraid that whether I'll be able to do time correlation function, but I think I'll be able to do linear response theory. So let us see. See, the reason I'm doing all these things, including hydrodynamics, kinetic theory of gas, essentially so that I can do linear response. Because I know very well, if I start with linear response, Liouville equation and perturbation, then it will not go down at all, the students. Because I know the students present days don't do any analytical work. They just do simulation, theory students. So require certain preparation of the understanding of random variables, preparation of understanding of time correlation function, then to at least appreciate that I must do the time correlation function. Otherwise, I'm doomed. I cannot understand experiment. So the laziness has no place here. You got to do some things. I'm writing a blog on, I have written many blogs on these students' laziness. My own students really complain that, you know, that what light it casts them. But this is not on that, it is on something else. But saying that, you know, you work hard when you enjoy something, and you don't work hard if you don't enjoy. That's essentially the theme, taking from one cue from Rituparna Ghosh's movie on Rabindranath. So, okie dokie, then.
Okay,
bye.
Thank you, Professor Bagchi, and also I thank everybody for being here and staying till the end, and we'll see you in the next iteration. So,
thank you,
bye.
Suman. Thank you.
Yeah.
Bye-bye.
Bye, everybody.